It's a search for a very rare physics process called neutrinoless double beta decay. Neutrinoless double beta decay is basically the products of beta decay are an antineutrino and an electron. And sometimes you can have what's called double beta decay, which is beta decay happening twice at the same time, so you get 2 electrons and 2 antineutrinos. But sometimes you can have, or at least theoretically, you can have what's called neutrinoless double beta decay, which is when you have double beta decay, except the 2 antineutrinos annihilate one another. And the only way they could annihilate one another is if the neutrino is a Majorana particle. And a neutrino is a Majorana particle if if the particle, so a Majorana particle is when a particle is its own antiparticle. So if a neutrino were a Majorana particle, then a neutrino is the same thing as an antineutrino. So they can annihilate each other. And this is a weird thing because if this were true, if there was a process called neutrinoless double beta decay, this would violate something called lepton number, and basically it means like whatever electrical charge you have at the beginning of the reaction should equal the electrical charge at the end. But if you didn't have any neutrinos at the end of the reaction, then lepton number would be violated, which doesn't go with the standard model as we know it. Observing this rare process would also give us a better idea of why there's more matter than antimatter in the universe. As we know, there's not equal amounts of matter and antimatter in the universe because things exist. Nothing, there are things that haven't been annihilated. So anyway, we search for this process using germanium detectors underground at the Stanford Underground Research Facility in Leeds, South Dakota. And so we have, I think, 29 germanium detectors that sit underground, about a mile underground. And the reason why we have them underground is this process is a very rare process. I think it happens, it theoretically happens once every 10 to the 25 years if you only have some mass of detector left running for a certain amount of time. I don't know the specifics, but anyway, we have germanium detectors, and double beta decay happens in these detectors, and so we want to observe the double beta decays that happen in these detectors to see if we can find neutrinoless double beta decay. But in order to do that, we have to eliminate any background detections that we could get. So, detections of cosmic rays, we'd have to throw out detections of other nuclear reactions happening in the germanium or outside of the germanium that ends up in the germanium, we'd have to get rid of. So that's why I have it underground, because so much stuff happens on the surface. We need to lower the background as much as possible. So that's why it's underground. The detectors sit inside, I guess the easiest way to say is a copper box, but the copper is pretty much the most pure copper in the world. It was electroformed underground. And no one has touched it, so it's very pure. So that limits background radiation, and then surrounding that box is a series of lead bricks that stack up and kind of form 4 lead walls around the copper box containing the detectors. And so we recently finished constructing this apparatus, and now we're taking data. The thing is, with the Majorana experiment we have, it's actually a demonstrator experiment, which means we don't intend to find neutrinoless double beta decay. What we want to prove is that we can achieve backgrounds low enough that if we built a bigger experiment with thousands of detectors, that we could do that and lower the backgrounds enough that we could find neutrinoless double beta decay in a time span that wasn't ridiculous, in a matter of a few years rather than 100. So hopefully this experiment will prove that we can achieve backgrounds low enough that we can build a bigger one. And if we build a bigger one, that experiment will be called Legend. And it will probably be housed somewhere in Italy, but that's to be determined. So that's the Majorana experiment in a nutshell. That made any
any sense.